So we're on 5.1, fundamental identities. The next chapter is about identities and solving and transforming trig functions. Now, how I view this is like a puzzle. You're playing a game. You're trying to manipulate, okay? That's what this unit is about. It's just like manipulation of the trig values, okay? If you think about it like that, it goes easy. I find it like to be like a little bit of a stress reliever. Try to transform them from one thing to another. You may not, but we're gonna roll with the punches. We're on trig. You're in the wrong class. All right, so our first identity that you need are our reciprocal identities. We've already talked about them. So we talked about reciprocal identities being that in sense of x's and y's, right? So cotangent is reciprocal identity is 1 over tan, right? Secant is reciprocal identity is 1 over cosine. And cosecant is reciprocal identity is 1 over sine. Yes, do we remember these? All right. Quotient identities. Quotient identities we also talked about already, but we talked about in terms of y over x, right? This is in terms of the actual value. So tan theta, which is y over x, y is your sine, x is your cosine. This is called our quotient identity, okay? Cotangent is going to be the reciprocal, which is cosine over sine, all right? We've done these before. We're just not going to be applying them in a different manner. All right. Yes. Are you with me? All right. So Pythagorean identities are what's semi-new. So do you guys remember when we wrote down x squared plus y squared equals r squared? Y'all remember that? And we said for a unit circle, it's going to be x squared plus y squared equals 1 because it's a unit circle, right? That means the radius is 1. Yes. All right. Now, from there becomes these identities. These are your Pythagorean identities. Remember, x represents cosine, y represents sine, correct? So from there became your Pythagorean identities. Now, someone took a lot of time and they took sine and cosine, interpret them into tan and secant and cotangent and cosecant and created the other two Pythagorean identities. This is your main identity, but these are the manipulations of that identity. You don't have to worry about how it got there. They're identities now, so they've already been proven and they're just accepted as fact, okay? So sine squared theta plus cosine squared theta equals 1. Tan squared theta plus 1 equals secant squared theta. And then you have 1 plus cotangent squared theta equals cosecant squared theta. These can be rewritten and manipulated multiple ways to find substitutions. So for example, if I wanted to get 1 by itself here, what would I do? If I wanted to get subtract. So we'd have 1 equals cosecant squared theta minus cotangent squared theta, okay? You can manipulate the identity to fit your situation. Does that make sense? If I wanted to get cotangent squared by itself, I would subtract 1, okay? Those are Pythagorean identities. Next are even odd identities. So your even odd identities are saying what trig values are going to be equal to each other, with one being negative and the other being positive. Well, the angle being negative or the actual trig value being negative. So for example, if I have a negative angle, that means that it's equal to the negative sign of the positive. And it just keeps going. Okay. So the pattern just continues. Okay, so you can see for our sine, our negative angles of sine, cosine, and tangent, it's going to change only for cosine. So when you look at cosine, the negative angle is going to equal its positive angle. Okay, whereas tan, it's going to be the opposite. No, we couldn't say absolute value because the value of cosine can still be negative. Yeah.
Well, what?
Like cosine, the value that it
Like
equals.
cosine -6 and cosine 6.
Yeah, it could still, or if you were at cosine of, what quadrant am I in? Cosine of 120. So if I was at cosine of 120 in quadrant 2, my cosine is going to be, the output's going to be negative because your x is cosine and it's negative. Like if you think about the unit circle and you're at cosine of 120, right? Your x value is going to be negative. That's why we can't think of it as a absolute value. Because cosine, the value can be negative. We have to. Okay, we'll apply it. But even at odd identities work as such. I'll let you write those down. Now, in trig identities, theta can be an angle in degrees, a real number, or a variable. Okay, it's just theta. We're not finding theta yet. We're just plugging it in. All right. So starting off here, it says if tan theta equals negative 5/3 and theta is in quadrant 2, find each trig function. Okay, so first we're going to start off with secant theta. Now, giving our notes, it tells us that tan theta is in quadrant 2. So it's in this quadrant, correct? Which means that I have a negative x and a positive y. Agree? Okay. When you have tan theta means that you are given your y and your x. Does that ring a bell? Do we remember that tan equals y over x, correct? So we have our y over our x. So when we're here, we know that which one has to be negative, the y or the x? The x. So that means that in terms of this, we have a positive sign and a negative cosine. Does that make sense? Because if I'm in quadrant 2, my sine is going to be positive, my cosine is going to be negative. Yeah? All right, next. From here, it gave us our values. What's in the numerator? What's in the denominator? And the negative applies to the 3. So from here alone, we know that sine theta of this angle equals 5. And we know that cosine theta of this angle equals negative 3. So if I needed to find secant theta, which one of these would help me find secant theta? Cosine, because it's what? What is the magic word? Reciprocals. Okay, so the reciprocal identity is secant theta equals 1 over your cosine theta. So what is the secant theta here? 1 over negative 3. So we used our quotient identity to identify what's sine and what's cosine. Then we use our reciprocal identity to find out what secant theta was. So this was our quotient. Why is cosine negative? Cosine is because it falls in. It's in quadrant 2. And in quadrant 2, that's where your x is negative. If it had been, if I had like sine of theta equal, then it would have been positive, yeah. Even when the but your cosine, everything else would have been, only sine is positive in quadrant 2. Everything else has to be negative, okay? Only sine and cosecant are positive in quadrant 2. Everything else is automatically negative. All right, let's try another one. So sine, we already know, right? So looking at the same one, sine theta, what did we get for our sine theta? 5, and that's it. So this equals 5, and it's positive because it's in quadrant 2. Okay. Where you felt the sine theta? I'm listening. Give another like, what other values would be negative? All values are negative except sine and cosecant because we're in quadrant 2. Wait, sine and cos are negative in quad 2, right? Sine and cosecant are positive in quadrant 2.
Yeah, so cosecant.
Remember, all students take calculus. It's the appropriate way of us saying it during a recording.
Oh. Positive cosecant or positive quotient.
Yes.
So it's 1/5.
Does that mean, huh?
Cosecant is 1/5.
Cosecant would be 1/5, exactly. All right, and then we can find all the rest, right? So we have, if I needed to find cotangent, just to check, can you tell me what cotangent of theta would be? It would be what? -3/5. Remember, it's the reciprocal of tangent, right? We have cosine, we have secant, we have cotangent. What's missing? Cosecant, right? And cosecant is a reciprocal of? You already said it, Justice? What was cos? Yeah, she already did it. Yeah. So it should be 1/5. Okay. So we have all 6 trig values just by knowing one and using all of our identities. So we used quotient and reciprocal identities, and we found all 6 of our trig values given one. Yes? Did we see how that worked? You have the quadrant, just make sure you know that you have the correct signs. Okay, because it's in quadrant 2, I know that the only thing that should be positive is sine and cosecant. Does that make sense? Okay. And as you can see here, are those the only 2 trig values that are positive? Okay. All right, now it says the negative. If I ask you for cotangent of negative theta, so looking at our identities, let me go back to it.
Okay, so like on the notes, right? It's saying some like negative through.
It says a lot of nonsense on the textbook notes. I would just stick to quotient, reciprocal, quotient, reciprocal. For that problem, because it's giving you tangent, and tangent allows you to use your quotient. They're gonna make you do Pythagorean identities for the textbook. Did they make you do Pythagorean identity?
Oh, for the first part.
Yeah, I said to do the Pythagorean. Yeah, I wouldn't. All right, so now it says cotangent of negative theta. So if I'm looking for cotangent of negative theta, what is the rule for that? Negative cotangent. And do we know our cotangent? What's our cotangent? Exactly. So if I'm looking for a cotangent of negative theta, it equals negative cotangent of theta. And what did we get for cotangent of theta? -3/5. And a negative times a negative makes a positive. So the final answer is 3/5.
Okay. So
we use the even and odd identity. Just showing you how an even and odd identity can be applied. So it gave you, since you know what it says, if I ask you for the cotangent of negative theta, right? That equals negative cotangent theta. Do we know the value of cotangent theta?
Yes.
Yes. So we substitute it in, we simplify, and we end up with 3/5. For B, oh, B was 5. B was just 5 because we use our quotient property. And we know that tangent is sine over cosine. So sine is our 5. And cosine was our -3. And we knew it was cosine that was negative because it was in what quadrant? 2. Okay, so that's how these 3 identities are used. Well, we didn't really use Pythagorean identity. Pythagorean identity would have came into play if we hadn't been given tangent, because it would have only given us, tangent gives us two knowledges, right? Sine and cosine are the basis of everything. Pythagorean identity would have been used, for example, if I had only been given sine squared, right? So if I'd only been given sine, I would have to use Pythagorean identity to find cosine. Then once I have cosine, I can find everything else along with it, okay? Yeah, so, but if you remember everything about X's and Y's, so you remember how we learned everything in terms of X and Y, 1/X, 1/Y, X squared plus Y squared. If you were good with that, you can interpret all of these into X's and Y's and just do just as fine. Okay. All right. So we're done with that one.
Like,
All right, it says write cosine X in terms of tan X, okay? So it wants us to write cosine X in terms of tan X. So when we think about this, we gotta think about which identity involves cosine and tangent. And the identity that involves both of them is we have our, what's that one called? You have your quotient, but that involves cosine and sine, right? Yes. So we know that tan X equals sine X over cosine X, right? That's quotient. However, it wants it only in terms of cosine. So would this one work? No, because it also involves sine. Does that make sense? Now, could you manipulate your way through this and get it in terms of it? Yes, which I'm going to show you. So I'm going to show you how to get it in terms of cosine from here. And then I'm going to do it the way that they want me to show you using the Pythagorean identity. Okay. So for me, I would set it up using quotient. With quotient, the goal is to get cosine by itself, like in terms of cosine, right? So if I need to get this in terms of cosine, I need to get cosine by itself. In order to get something by itself, you have to get it out of the denominator first. So if I want to get this out of the denominator, what would I need to do? Multiply. So I'm going to multiply both sides times cosine X, right? When I multiply, it
you don't want 1/sin X?
still wouldn't have gotten that out of the denominator.
It wouldn't have?
If I multiply by 1 over sine X, it would have just canceled out the sine. My goal is to get cosine out the denominator. And now I'm going to divide by tan. So cosine X equals sine X divided by tan X. So what happens here? What is tan again? Tan is sine over cosine, correct? So that means that I have sine X over sine times X, divided by cosine, I'm sorry. How do you multiply fractions? I'm holding.
You said it's sine over cosine?
Why is the sine divided by cosine?
Substitution. 10x equals
Keep change flip.
keep, change, flip. We change, we keep the numerator, we change the multiplication, and we flip the denominator. Does that ring a bell? When it all comes down to it, I can say cosine X equals cosine X. This is why if we start with the quotient function, it's going to end up saying, okay, is this a true statement? And is it a true statement? Does tan X equal sine X over cosine X? Yes, someone proved it. We made it in terms of cosine. And if we reversed it and did in terms of sine, then it would all come together and keep going back and forth, right? Now, this is why we can't use the quotient function, because if we use the quotient function, it's just going to take us in a circle. And it's
Right.
to show you that sometimes it's the easy, you think it's the easiest way of doing it, and I want you to see aware of possible mistakes that you may make. Okay, now, this is where we're going to use our Pythagorean identity. Now, we're going to be using this guy. 1 plus tan squared x equals secant squared x. And this is one of our, I'm always worried that I spelled that wrong. Is that right? Yes, it is. I think it is. Pythagorean. Yeah, you know what I'm saying. Okay, so it says it wants it in terms of cosine. That means that it wants me to replace, it wants me to get tangent by itself and get rid of secant. Well, how can I change secant into cosine? Yeah, say it. 1 over cosine squared. Good job. So we get 1 plus tan squared x equals 1 over cosine squared x. And now it wants us to get tan by itself. What are the steps to get tangent by itself? Subtract. Subtract what? The 1. So now tangent's almost by itself. What's the last step to get tangent by itself? It says tan squared. So I'm going to take the square root. So we get that tan x equals the square root of 1 over cosine x minus 1. And that's where you stop at, because now it's tangent in terms of cosine only. And the answer is yes. Why is this beneficial? This is beneficial because if I know the cosine value of it, I instantly can find the tangent value. Or depending on if I'm trying to eliminate something, or the problem that I came down to, simplify it to this. But this is tangent in the terms of only cosine only. I don't need to know anything else. As long as I know the cosine, I can find the tangent. Because it said write cosine x in terms of. Oh, I went the wrong way. We'll do both. So now, what if I wanted to get cosine by itself? So now we were here at 1 plus tan squared x equaled 1 over cosine squared x. What are the steps I would take to get cosine by itself? We have to multiply, right? Agreed or disagree? Agreed. So we're going to multiply both sides times cosine squared. So we get cosine squared x times 1 plus tan squared x equals 1. Okay, now how do I get cosine by itself? We multiply by cosine squared x. We're going to divide. Good job. So I'm going to divide by this guy. 1 plus tan squared x. So we get cosine squared x equals 1 divided by 1 plus tan squared x. And then the last step to get cosine by itself, take the square root. So cosine x equals the square root of 1 over 1 plus tan squared x. So now we have cosine in terms of tan, we have tangent in terms of cosine. So depending on what the problem's asking or what you're solving from here on out, you can plug and chug. Okay? The purpose of equations and isolating a variable is so that you can plug and chug things in, pretty much. Once you have more information. Now, can you do anything without knowing what the angle is? Nope. All you can do is set it up and be ready. Okay? Remember I told you in the beginning, this is a game of really? Why? Why would charades the thing? Yeah. Oh man. All right, so the red side is tangent in terms of cosine. The purple blue side is cosine in terms of tan. I say, sure, are you okay? All right. This says that we're going to write, we want to write this in terms of strictly sine and cosine only. I told you, it's a game of manipulation. It's just a plug and chug and use your identities. Your identities are your puzzle pieces. Okay, so your identities are your puzzle pieces. And it wants us to rewrite this with only sine and cosine. So first thing first is we got to replace cotangent. How can I replace cotangent with only sine and cosine?
It's gonna be what, sine over cosine, 1 plus sine over cosine.
Reciprocate.
Oh, cosine over cosine.
There you go. So-
X over y?
Remember, it's cotangent, so it's the reciprocal
Oh,
of tangent.
Oh.
So we have 1 plus cosine over sine, and they're both going to be squared. When I'm doing this, I don't like writing the theta. Will it bother y'all if I don't write the theta into the end?
No.
Okay. All right. How can I turn cosecant into terms of sine or cosine?
How can you turn what?
Cosecant into sine or cosine. There you go. It's going to be 1 over sine squared. So we have 1 minus 1 over sine squared. Okay. So first step is to replace using your identities. So the first identity we used was our quotient identity. So here we use quotient. And here we use reciprocal. Agreed? How you spell reciprocal? You get it. All right, next, it wants you to simplify. Simplify means to reduce all fractions and get down to one single fraction if possible. Okay, in your numerator, how can I make that into one fraction?
Huh?
How can I make 1 plus cosine squared over sine squared into one single fraction? No, you're gonna do y'all remember me saying chopsticks in a bowl? Or quick adding of fractions? Let's chopstick it out. Here we go. So chopstick, here's my first chopstick, 1 times sine squared, which is what? 1 times sine squared? Sine squared. Here's my rice, plus. Here's my other chopstick to pick up my rice. 1 times cosine squared is cosine squared all over my bowl, which is 1 times sine squared, which is sine squared. Okay, this works for adding and subtracting any fractions. So for example, if you had 1/2 minus 3/5, to chopstick it out, 1 times 5 is, minus 2 times 3 is, all in the bowl, 10. 5 minus 6 is -1 over. Okay, that's how chopsticks in a bowl work. You see the chopsticks inside the bowl? Okay. We're going to repeat the chopsticks in the denominator. So now we're going to go to the denominator. We're going to make this into one single fraction. So again, 1 times sine squared is sine squared. My rice is minus 1 times 1 is 1 all over sine squared. Okay. Then you keep simplifying. Sine squared plus cosine squared is what? What is sine squared plus cosine squared? It equals what? 1. So this whole thing can be replaced with a 1.
I'm tired of this. Why can't, like, you?
Told you they're puzzle
Look at it
pieces.
and it's like, oh, that's 1.
You did. You have to learn. Like I knew it was 1 instantly, but I had to go through the math with you. Okay. And this is, why is it 1 again? Because it's a Pythagorean. Okay. And how do we divide fractions? Keep, change, flip. So I'm going to keep 1 over sine squared. I'm going to change from division to multiplication. And then I'm going to flip sine squared over sine squared minus 1. And what do you notice happens? They cancel. Said so angry. So we're left with 1 over sine squared minus 1. Looking at your Pythagorean identity, we have sine squared plus cosine squared equals 1. So what would sine squared minus 1 equal? Keeping this in mind. It would equal what kind of cosine? It would equal negative cosine. So your final answer is not negative cosine squared theta. And that is your simplified answer with no quotients. Because it's set with what? No quotient.
What did you do?
We use the Pythagorean identity. So keeping in mind sine squared plus cosine squared equals 1. If I, which part?
That one.
This part? So here we keep, change, flip. We kept the numerator, change the sign, flip the denominator. And like then someone said to cancel. We have the same thing in the numerator and in the denominator. They cancel each other out. And we're left with 1 over sine squared minus 1. Then we use the Pythagorean. If I was to make this look like that, what would be left? So if I subtracted the 1, that means I would have to subtract the cosine. So my final answer. Okay. So sine squared minus 1. It's really, I'm telling y'all, I know this is gonna be the most frustrating section because it is a puzzle and puzzles can be frustrating. And this entire section is puzzles. Okay. Now this is where the puzzle piece comes into play. So this is our Pythagorean, right? Remember I told you the Pythagorean can be manipulated to look like whatever you need to look like. An identity can change. If there's a way for me to make this look like that, what would I be left with? So if I subtracted the 1, right? That means I would have to subtract the cosine. So it would be sine squared minus 1 has to equal negative cosine squared theta. Oh, sorry. I brought my 1 over.
Since we're using sine
Okay.
and cos, can you automatically?
And then therefore this just equals, huh?
Since we're using sine and cos in like the equation, can't we just automatically say what we want?
No. They only equal 1 when they're being added together and they're squared. So sine squared plus cosine squared equals 1, but not,
Sine squared minus cos.
yeah. I told you I hate teaching this section. But because cosine, reciprocal identity. I wasn't there yet. All right. So again, my warning about you this